So now let's look at 7.5, solving initial value problems using Laplace transforms, of course. So here's the method that we want to go over. Sometimes I write this out, but sometimes I like to write it and discuss as we go. So the method. So this is what you do, and I'm paraphrasing probably what's in the book. So just to recap a little bit, actually, going back to here, this was the inverse Laplace transform, basically to get to this form, this solution. And so when you have your function in this form, then the inverse allows us to go back. And so you really don't continue to perform the inverse Laplace transform. A lot of it's looking up using the properties and looking up the formulas to have you go backwards. So keep that in mind. And then there's a lot of stuff going on that you wouldn't necessarily like memorize. So you would say, okay, what is that? But you know where to look it up. Okay, so 7.5. First thing you do is you take the Laplace transform, let's say L, of both sides of the equation. Okay. And then you're going to have terms and constants. So you use properties of Laplace to solve. So use properties of the Laplace transform to solve and use the initial conditions. So you'll have like y prime of 0 is 1 or y of 0 is 0 or something. And when you use that, and you'll see, let me go back here real quick, you'll see when you have this Laplace transform, you have these cases here. So if you look at f prime, this is the expansion of it. And so you might have that f of 0 is 0 or whatever. Similarly here, if double prime, you have a prime here. So it's maybe given that f prime is something, and then you evaluate that. So it's almost like you're evaluating the initial conditions before you continue to solve. So that's why these are considered initial conditions. It's not a general solution. You never get a general solution on these. That's what's a little different. Okay, C. Determine the inverse Laplace transform. So you'll look that up. So determine, you might have to do something, but determine the inverse Laplace transform by table or an additional method. So I'll just say by table or method, or you could write additional method. For example, partial fraction decomposition. Okay, so let's look at an example. So solve y double prime minus 2y prime plus 5y equal to negative 8 e to the negative t. And then it's given that y of 0 is equal to 2 and y prime of 0 is equal to 12. Why they have to make it difficult with 12, I don't know, but that's what the question was. So this is a differential equation. So we've seen this type of form before. There's other ways to solve it. But this is basically how to use a Laplace transform to solve. So this is like an integrating factor kind of concept. It's a way to manipulate the equation into something that we can simplify and solve. So it's like you're rewriting it in terms of the Laplace using all the properties we just developed. All right, so then you just do Laplace transform of both sides, and I'll write this one all the way out of that whole thing, y double prime minus 2y prime plus 5y equal to the Laplace transform of negative 8 e to the negative t. So from here, you can see that you can express this by the linearity property, and then you have the factor out the constant. Okay, so we're going to do that next. And so you get this is equivalent if and only if. You get the Laplace transform of y double prime of s. And that really would be in here, actually. I forgot to put the of s. I want to keep the notation consistent. And you can like make substitutions and not have all of this notation, which I do on another question. No, I think I do it on this one. Make it a little simpler. Okay, so now we use the linearity properties and constant multiple. So you get this of s plus 5 Laplace transform of y of s, and then equal to the right-hand side, take out the negative 8, e to the negative t of s. So then, with each of these, we have, and just keep in mind, just might be clear, but y is f, right? So when you look at this back here, you're really just replacing the f with the y. So now we're going to do this expansion and use the initial conditions. So let me bring that down in case I need to point to that. I'll bring it down when I need to. So let's do that for each one. Use the Laplace transform of those derivatives. So this is change colors there. This is equivalent to s squared, and then the Laplace transform of y of s, and then it's minus s y of 0 minus y prime of 0, and then minus 2 times s Laplace transform y of s minus y of 0 plus 5 times Laplace transform of y of s, and that's not much left here, equal to, so that the next one, you look this up, so you have the negative 8, but then e to the negative t is just s plus the 1. So you get negative 8 over s plus 1. So that one I went ahead and evaluated. So to simplify things, what we're going to do next is we're going to let L of y equal just capital L. Actually, the of s as well. Let me put that down. L of y of s, we're going to let it be capital L. So you can do that. think I've already seen you guys do that. Anyway. So we get this equal to or equivalent to, and let's see, did I simplify this? No, I just rewrote this with that just because it makes it look simpler to look at. You can factor it and stuff, combine like terms. Oh no, I did evaluate. So I'm missing a step here. Hold on a second. Where am I at? No, I think I'm good here. Well, just to point out this, let me show you this part. Okay, so this is the what we're going to substitute. Okay, so y of 0 is 2, and I did want to point this part out actually. And then, before I move on, y prime of 0 is 12. So we do that substitution next. So let me just try to do this one all the way out in detail. So now substitute for those initial conditions. Oh, one more. Wait a minute. Forgot about this guy here. All right, so those we're going to substitute for. And we can go ahead and do our L as well. Let's just do that next. So that's s squared L minus, and then y of 0 is 2, so it's 2s. And then y prime of 0 is 12, so it's minus 12 minus 2 times, and let's put in parentheses, s, and then L minus, and what is y of 0? It's 2. And that's then plus 5 times, and we're calling that L, equal to negative 8 over, oops, I was going to write a 5, over s plus 1. Okay, like that. So now we look at our L's here, here, and here, and we can expand collect like terms and factor out the L, and then solve for it, because that's your, and then you just take the inverse transform of that. So let's continue then. So I can write down some steps for you. Okay, so expand, collect, solve for L. Okay, so that's what we're doing. And then you'll see it's in a nice form that'll mimic what's above. And then you take the inverse transform of that. So you can pause and do that if you want at this point. So you get s squared L minus 2s minus 12 minus 2sL plus 4 plus 5L equal to negative 8 over s plus 1. So now let's go ahead and collect like terms. I know you can see this already. I'm pretty sure you're like right there with me. But so now let's collect like terms there, and bring, and then everything else you bring to the right hand side. So we get this equivalent to, and we can go ahead and factor that right away, can't we? We can just say it's s squared minus 2s plus 5L. And then let's bring it over to the right-hand side. Equal to 2s. And then let's just add those up. So that's going to be my negative 8. And so you get a plus 8 over here. So it's plus 8. And then minus 8 over s plus 1. There we go. So now it's looking nicer, isn't it? So now we can add that up and continue to simplify. So you get, this is equivalent to s squared minus 2s plus 5l. And then get a common denominator there. So you're going to have s plus 1. So you basically are just going to say each of those is s plus 1. Actually, let's just do this. Say this is equal to 2s s plus 1 plus 8s plus 1 minus 8 all over. Why did I do that? Sometimes I love this, sometimes I hate it. S plus 1. And so I'll use this step in simplifying that. So you get 2s squared plus 2s plus 8s plus 8 minus 8. Oh, those are going to cancel. That's when you can say cancel, by the way. And then let's keep going. That's 2s squared plus 8, 9, 10s all over s plus 1. Okay. So that is equivalent to, so let's go ahead and we'll just divide now and get L. So L is equal to 2s squared plus 10s all over s squared minus 2s plus 5 times s plus 1. So that is your Laplace transform. That's the Laplace transform of y of t of s. So that's, did you see how that, so that substitution made it a lot nicer. But you don't want to lose track of that it's a Laplace transform and all that. So that's why you want to put that in. So now find the inverse Laplace transform. Okay, using partial fraction decomposition. So that's probably one very similar to one we would have seen. And I'm not going to work that one out. So that let's just go back up for a second here and see if there's one similar. So here's one, but this one has quadratic in the numerator, and then here's your partial fraction, and then this is your denominator. So to do, let's see if there's anything else that's similar. So yeah, I didn't even do one that's that complicated with partial fractions, because let me show you this. This would take some work. Excuse me. Those are just allergies, by the way. This is an irreducible quadratic. So when you solve this one, you're going to have one term with a over s plus 1. But your other terms use that irreducible quadratic thing. So it's going to be bx plus c over that, or they use that process. So that one takes some time to do. And at this stage, just try it, but I wouldn't worry about it too much. Just it's really this process above you need to get that's new. Unless it's a quiz, of course. I think that quiz has something. So using the Laplace transform, and you get y of t, and it ends up being this. So this I'm just giving you. So it's 3e to the t cosine 2t plus 4e to the t sine 2t minus e to the negative t. Okay, and again, that's a whole nother technique to do that. That would take another 15 minutes or more to evaluate that. But it really is just a partial fraction decomposition, and then you're applying the properties to those individual terms. You're going to get something like this, and then you have properties to know what they equal. So it's a little more scripted at that point. Oops, too far. Okay, we'll do another couple examples in the next video.